Alright, the purpose of this video is to explore power series and convergence for power series. And so what makes a power series special is that we allow the series to contain a variable x, where x can be any real number, just like a function, like f of x. So we can let x be any real number, but the k value represents a power. So if we have x to a power, where the power is ascending from 0 or 1 or wherever our starting value is, up to infinity. Now there'll be other factors working into this particular power series. In this case, we're going to divide by k factorial. This produces a sequence, or series rather, that would look something like this. We notice that when k equals 0, we have x to the 0 over 0 factorial, which is 1. Then we have x to the 1 over 1 factorial, and so on. By the time we get to 3, x equals x to the third over 3 factorial, which is 3 times 2 times 1. So this series will continue on and create a polynomial that goes on and on for infinity. And again, which values of x are going to allow this particular series to converge? And that's what we're going to do. Now, for radius of convergence with power series, there's one algorithm that we have to know, and that's basically the limit comparison test. So we are going to compare two consecutive terms within the sequence, use of k plus 1 over use of k, and then we're going to take the limit as k approaches infinity of that particular ratio, and if that limit approaches 0, we can say that we have convergence for all values of x. If the limit equals something else, we'll explore that later in this video. Dividing by a fraction, we multiply by the reciprocal, and that creates a convenient situation in two cases. First of all, the k to factorial divides with every factor of k plus 1 factorial except the first one. And the x's are same bases. We subtract the exponents for the quotient rule, and we're left with x to the 1. Then, as we take the limit as k approaches infinity, we see the denominator increases without bound, forcing the limit to be 0. What that means is this series will converge for all values of x. It doesn't matter what I choose. If this is 5 plus 5 squared, if this is 5 plus 5 squared over 2 plus 5 cubed over 6 plus and so on, we can still guarantee that the factorials in the denominator are eventually going to overpower the powers in the numerator, and hence create a convergent sequence for all values for x. Finding the radius of convergence for another series, keep getting those mixed up, would look like this. But this time we have k to the fourth. K is now the base, and 4 is a fixed exponent. X here is a variable, and it's a k ascending power. So that's again what defines as a power series, and k plus 1 factorial. Identifying two consecutive terms in the sequence in general. Careful, and this time we're going to have k plus 2 and k plus 2 factorial because we're adding 1 to the k. In the ratio, I'm already going to take the reciprocal of the denominator, so I get this ratio. And just to keep my work looking clean, I'm going to demonstrate how k plus 1 to the fourth over k to the fourth, x to the k plus 2 over x to the k plus 1, and k plus 1 factorial over k plus 2 factorial. Each of these is a clean ratio that we can divide out nicely. Here we'll use power of a quotient to divide and then take to the fourth power. Here we subtract the exponents and get x to the 1, and here again we have all the factors dividing out except for the first one of the denominator, k plus 2. Here I'm going to distribute the k. I divide out k, and I get a form like this. And now as I let k approach infinity, I will observe this base approaches 1. So it's 1 to the fourth, or 1. K approaches infinity, this becomes 0. So this is a very similar situation to what we had in the previous example. All this extraneous information here doesn't have any bearing on the convergence of this particular series. In this series, we might find something a little bit more interesting. So what we have is x minus 5 this time instead of just x to the k power. And here we have the square root of k times 2 to the k power. Now, what's interesting about this is we have exponential growth in the denominator, but we also have exponential growth in some circumstances in the numerator. A situation where we have exponential growth is any time where the base of this particular power series is bigger than 1. If, however, this particular number inside the parentheses is less than 1, then we have a situation where... Sorry, I'm parked outside at the moment, and there was a service vehicle just pulling up next to my car. It was very loud and distracting, so I lost my train of thought, and I apologize. But I think what we were talking about here, what I was talking about or trying to, was if the base of this particular number ends up being less than 1, then taking it to ascending powers is actually possibly going to cause 0 numerators, which will 0 or converge the sequence. So there are probably x's where this will converge, and our job is to find the radius of convergence, that is the band above or below 5 in this case, that we can use as convergible x's, if you will. That will lead then to our interval of convergence. Once we know the radius of convergence, we're going to add and subtract it to 5, and that'll tell us which band of x's will make this a convergence series. So let's see what happens. Once again, we observe 2 consecutive terms of the sequence. I'll compare them in a ratio. And in this case, again, I'll reciprocate the u sub k term. And making the same kinds of comparisons here, same bases. We just have to subtract the exponents. Here we can combine the roots, and here we can subtract the exponents as well, and get some really nice, clean results. So, this time we do have something a little bit more interesting occurring. As we allow k to approach infinity, this approaches 1, and this approaches, well, it's a half. So the only thing affected by k is the square root of k over k plus 1. We can see how it's going to be, regardless of that plus 1, this will still get closer and closer to 1, actually really quickly. So what I end up with is the series converges. Sorry, I was distracted by my own writing. This is essentially the limit as k goes to infinity. What we want to have happen to that limit is we want it to be less than 1. If it's less than 1, then the ratio shows a convergent geometric series. If this limit is larger than 1, then we're going to have a divergent series. So basically I just have to say whatever I choose for x has to form something that's smaller than 1 in ratio. A little bit of algebra, we double both sides. This shows our radius of convergence. We are starting from 5, and we are going to be 2 units above or below 5. If x is within that band, that is to say from 3 to 7, then we can claim convergence for this particular series. So that is almost the interval of convergence. The only problem is that we have to check the endpoints, because there might be some interesting stuff happening when x is 3, when x is 7. Observe. Oops, that was more than I wanted to reveal at once. We start with x equals 3. When you substitute 3 in for x, you end up with 3 minus 5, which is negative 2. It's negative 2 to the k power over the square root of k times 2 to the k. This happens to be an alternating series, because depending on whether k is odd or even, the numbers we add are going to be positive or negative. There's only one thing to do for alternating series, and that's to do the alternating series test. Before I do that, I just want to point out the correct form. We pull out the negative 1 to the k power to show the alternating portion, and then we've got 2 to the k over 2 to the k, which cleans up real nice. That is an alternating series, so we're going to do the alternating series test. First thing we need to do is to prove that u sub k plus 1 is always going to be smaller than u sub k. That is to say, is the sequence decreasing in value for a large enough number of k? Here we can see clearly that the denominator of this fraction is always going to be bigger than the denominator of that fraction, therefore we're going to have a smaller ratio for all values of k that are positive. So the next thing to do is to take the limit of the sequence, u sub k, as k approaches infinity. In this case it's 0, and since the limit approaches 0, And here we have a decreasing function. It approaches 0. We can now claim convergence on this particular alternating series. So when x equals 3, that is also part of the interval, the convergence interval, or what was that called again? Interval of convergence. Alright, so now we check for when x equals 7. When x equals 7, we no longer have an alternating series, so we cannot obviously use the alternating series test. What we have here is a divergent p-series. It is enough to identify or claim that this is a divergent p-series because p is less than 1. We can stop now and give our final conclusion. The series converges when x is larger than 3 and smaller than 7, including 3 but not including 7. So we can use either of these notations. In calculus at higher levels, this is the preferred notation, so we can use that. So the idea is x can be within 2 above or below 5 and still converge, and we can also include 3. I believe this is the final example for this video. Find the interval of convergence for 5 times k times x plus 4 to the k power. So we're going to have increasing coefficients as well as increasing powers here, and so let's find out when this thing converges. Once again, we look at the x plus 4, by the way. We should know that if there is an interval of convergence, it's going to be above or below -4, the root of this particular base. And so in the issue, interval of convergence, is a radius of convergence rather, that's essentially going to be how far above or below 4 can we go and still have a convergence sequence, series, sorry. Here again we see putting the ratios together. In this case I don't even have to multiply by the reciprocal. 5's divide out to 1. K plus 1 over k is here, which I distribute the k to get that form. And here we just subtract the bases, or subtract the exponents again, and get x plus 4. Now when we allow k to approach infinity, we end up with 1 times x plus 4. In order for this to converge then, our common ratio, the r value that produces this series, has to be less than 1. So, when does that happen? Well, if x plus 4 is less than 1, then x is between -5 and -3. So here we can see the radius of convergence is 1, which is essentially going to be that coefficient here, and we could be 1 above or below within that band and have a convergent series here. Now, once again, we have to check the endpoints for -5 and -3 specifically. So here's our series. Check it again when x equals -5. This time we get 5k to -1 to the k. This diverges, even though it's an alternating series. We can see here that 5k, we let k go to infinity, it's going to become infinitely large, or that is, we cannot define its limit. And here, more obviously, we're divergent at that point as well. So in this case, our interval of convergence does not include the endpoints. It's open interval from -5 to -3. Alright, I hope that's helpful. Good luck to you all.